Hi, welcome to your lesson on the normal distribution, coming to you live from a small lodge in rural Lithuania. Okay, let's begin. Let's begin with this question. Which histogram below do you think is a better representation of the heights of students in our high school? Well, maybe you answered this one, maybe the second one. Who knows which one you answered, but let me give you a little insight here. Where we have a small sample of students, such as our high school group, it's not that many, we can see all kinds of variation. We can see outliers and things like that. So for example, here we see a few outliers on the short end of students, and this part here, there's some more taller students here, and a few more here, less here. Anyway, there's more variation there, whereas this curve, or this histogram, is a perfect normal distribution. So when we have a small sample, you can see more variation. But when you have a large sample, like for example, this second question, what if we found the heights of thousands and thousands of students across Europe? Well, in that case, when we have a large sample, you would see something more like this, because height in general around the world is distributed normally, like this. And if something is distributed normally, it will have this perfect bell-shaped curve, something like this. Whereas if it's not normal, it's going to be a little bit more erratic. And that's just like when we began probability. We talked about theoretical probability and experimental probability. When we run an experiment, there can be lots of variation. But as we increase the number of trials in our experiment, the variation kind of gets eliminated and we move closer to theory. So in theory, heights should look like this. So the larger the sample we have, the closer it will get to that perfect bell-shaped curve. Let's take some notes now on the page that was provided to you. Of these then, based on what we just talked about, of these five, which do you think look like normal distribution? Well, maybe you answered the last two. Perhaps you thought this one as well because it looks like they approximated that bell-shaped curve there. But even though they put that there, I think this one's a little too far from looking like a normal curve, whereas the last two, they look pretty normal. So when data is normally distributed, statisticians use a normal curve. So again, when it has that shape, your histogram of data, you can use a curve then to approximate that. For the next little bit, just listen, and we'll take notes a little bit later again. Okay, so there's many distributions in probability, so many here, but we're focusing right now on this one, this single one here, the normal distribution. It is also called the Gaussian distribution. Let's take a look at why. So the normal distribution is probably the most important distribution in statistics, since it is since it is a suitable model for many naturally occurring variables. These include physical attributes of people, like we just said, height, for example, or weight, animals, plants, and even mass-produced items from factories. The distribution could also be applied as an approximation of student exam scores, times to complete a piece of work, reaction times, IQ scores. Again, this is a very common distribution. For example, we have very few on the low end, few on the high end, and most people somewhere around that expected average. And it's called the Gaussian curve because it's named after this person right here, German astronomer, physicist, scientist Gauss. And you can see here is his Gaussian curve. So it's right on this 10 Deutschmark note. So the normal curve, also called the Gaussian curve, after the German mathematician Carl Friedrich Gauss. Gauss used the normal curve to analyze astronomical data in 1809. In Germany, the portrait of Gauss appears on the Deutschmark note, which we just saw right here. Although Gauss played an important role in its history, the French statisticians Abraham de Moivre and Pierre-Simon Laplace were involved in much of the early work. De Moivre developed the normal curve mathematically in 1733 as an approximation to the binomial distribution. Okay, we've just looked at binomial distribution. Let's take a look at why the normal curve is used in relation to that. So you remember seeing a video of the Galton Board. Let's just remind you guys of that one. It's important to see. So here it is. We can see all the balls flowing through these pegs. Oh no, it's having trouble. Okay, so the balls, and each time a ball hits a peg is a choice. It can go left or right. So it's like a binomial choice. Two choices. And in this case, there's a 50-50 chance it will go one way or the other. And then as the balls collect in the bins below the pegs, we can see the balls collect in this kind of shape. Oh, that's starting to look like a normal distribution. It's definitely looking like a normal distribution. So There's the final shape there. So for some reason, most of the balls congregate in the middle, and only a few balls end up on each end. We talked about the idea already. The reason very few balls go to the end is because going to the end would mean always bouncing one direction. For example, left, 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 left. And it's very unlikely it will always make the same choice of bouncing that same direction, and likewise to the right. Most balls take a path that goes left, right, left, right, left, right, or something like that, and end up in the middle. So we ran that simulation on an online simulator as well, and we confirmed, yes, most of the balls will end up in the middle. Very few will take those bounces, that journey that includes all the bounces the same direction. We also then adjusted that, because the question is, does this work for every binomial distribution? Would it always look like this? Well, if you remember, we adjusted the pegs. Notice that these pegs have a slightly right-facing tilt. So now the balls are a little bit more likely to bounce to the right. So instead of having a 50-50 probability like here I changed it, I think, to 65% right and 35% left. And in this case, notice the balls accumulated this way. It still looks like a normal distribution, but it's shifted to the right. Basically, the mean, which used to be here, is now here. So it's still a normal distribution that can represent that, even when you change the binomial probability. So that's why the normal curve is an approximation, or was used by Gaussian Board and others as an approximation of normal data, because basically the normal curve does represent binomial distribution outcomes. Okay, so the next question then is, if you have these bars here, and each of those represents a certain number of balls. For example, here 61 balls ended up in this bar here. So that's 61 of whatever the total number is here. Let's say it's like 300 or something. And that can give us a probability of a ball ending up right here. So if each bar represents a probability, then once we make a curve to approximate that, then an area under the curve can represent the probability. For example, if you want the probability of a ball ending up in these 4 zones here, you could just find the area of those 4, and that area out of the possible total area of 100% will give you your probability. Okay, so that brings us to a very important idea. Let's take a look at this big idea in mathematics. We have a normal distribution, and to find the probability of something occurring, we just have to find the area under that curve. Reminder, some notation. If a random variable x is binomially distributed, we write it like this, right? Random variable x distributed binomially, and here we write the number of trials and the probability. Now we're talking about a new notation for normal distribution. So if a random variable x is normally distributed, we write it like this: normally distributed, and in the brackets here, instead of trials and probability, we put the mean and the standard deviation squared, which is the variance. But we can usually see it written like this, something squared. So this number will be your standard deviation. Okay, let's take a look at how that works. So again, that's the mean, and this is the variance. So back to our notes page. We're ready to take some more notes. We have a normal distribution curve here, and this is just to get you used to with how these things work. So data, it says, is normally distributed with a mean of 14 and a standard deviation of 3. So if the mean is 14, which of these little marks will you write the mean beside? Will it be this first one here? Or sorry, I guess this is the first one, second one, third one, fourth one, fifth one, sixth one. Okay. Well, hopefully you're thinking, since this is normally distributed, first of all, we can write it like this, our normal distribution. We have a mean of 14, standard deviation of 3, so we write 3 squared because that represents the variance. Okay, so the mean goes here. It's right in the middle. That's the middle of the data. Imagine that being the middle bar if this was still a histogram. And standard deviation is 3, so what is the number that's going to be here and here? Well, hopefully you're thinking, okay, standard deviation, 3. I know we haven't talked about this yet, but maybe you're thinking I can use that 3 to get that. Likewise, jump 3 more, and then 3 more. And then from 14 going down, 11, 8, and 5. So this is how we generally set these up. So mean is here, and then each jump of standard deviation, you can write the number here. So one jump of standard deviation, 17, another jump, 20, and so on. That's the normal setup. So now that you've seen that, set this one up. What are the numbers on all these little bars going to be on the bottom here? Well, writing out the distribution here, we have normally distributed, mean of 97, standard deviation of 13, making a variance of 13 squared, 97, 110, 123, 136, jumping up by 13 every time, and then going down by 13 every time. Okay, now looking at this, can you sketch a distribution on the same picture here that has a higher mean but the same standard deviation? Well, I hope you sketch something like this. It has the same shape because the deviation tells us how much it's spread out. So this curve shows the same spread, basically the same width, but the mean has shifted forward, so the mean is higher. Here's some more examples of something like that. We have 3 different distributions there. Notice these all have the same standard deviation, the 2 squared there, but the mean is different, 5, 10, 15. So you can see again, same shape, but mean is 5, mean is 10, mean is 15. Okay, next one. On this one, can you sketch one that has the same mean, that should say mean, but a higher standard deviation? Okay, same mean. Notice I drew the curve just above the same one there. They have the same mean here, but the one I just added is more spread out, therefore higher standard deviation. Again, see, more spread out. Okay, so here, again, we have the same kind of example. We have 3 distributions. They all have the same mean. You can see 5, 5, 5, but the standard deviation is changing 1, 2, and 3. So this one has a smaller variance, bigger variance, and the blue one has the highest variance. It's most spread out. Okay, now final one, sketch something with a lower mean, but a lower standard deviation. Okay, the mean shifted, see the middle shifted, and it got more narrow, so lower deviation, lower spread of data as well. Now, amazingly, the area under a full standard normal curve is exactly 1, right? That area under this whole thing is 1. Why? Okay, I hope you answered, because if it was drawn as a bunch of histogram bars, a bunch of data, then the area of all those would be 1, because each one represents a portion of the probability of the total of all the events, right? So all the possibilities add up to 1. So in this case, when you look at what's shaded here, if somebody said, tell me the probability in this case of getting something that is 5 or under, well, you look at that blue area there, and that blue area will give us the probability of something, whatever this data is, having a result of 5 or under. So with that, if we can know the area under a normal curve, we can find the probability. So let's look at some main areas here. When we talk about, look at these first part here. So here's our mean, and here it says mean plus 1 standard deviation or mean minus 1 standard deviation. So when you are within 1 standard deviation of the mean, this whole area has an area of 68.27%. That means 68% of the data lies within that zone, 1 or standard deviation away from the mean. Okay, now if you are 2 standard deviations away from the mean, that's what we see here. 2 more or 2 less than the mean. So that whole zone there where you're within 2 standard deviations of the mean, that's 95.45% of the data. And finally, if you're 3 standard deviations from the mean, notice that when you're 3 away, there's very little bit left beyond there. Yes, the curve will continue, but so little of the area remains beyond there. Basically, you have 99.73% of all the data within 3 standard deviations. So that tells you something about normal data. That basically, normal data means that most people are, like most of the data is centered around the mean, and very few are bigger and very few are smaller. It's all around the mean, right? 68% of the data is close to the mean within 1 standard deviation. Okay, so for example, if you had a 55 kilogram student and we were told the standard deviation is 12, you could add these numbers here, add 12, take away 12, add 12, take away 12. So just like we looked at before. And now we could say, okay, well, we know most students are around 55 kilograms, and actually 68% of them are between 43 and 67 kilograms, because that's 12 below and above the mean. That's the standard deviation. So most students, 68%, are within that zone. And 95% of students are from 31 to 79 kilograms. Okay, so that's your introduction to standard deviation. We're ready to apply this and do some problems and also use our calculator. So this was part 1 video. Please prepare yourself for the next video, which will now take you into some problems where we apply all this knowledge we just learned. Please join me in video 2 very soon.